There are several pieces of this that you need to be paying attention to, but also there are pieces of other things we've talked about that are going to influence our questions. And the first thing I want to point out is that just because we're on a new topic doesn't mean we forget the old topics. If I drop a ball from 10 meters and I tell you that it recoils off of the ground only 7 meters, I can ask you for what the impulse imparted to the ball from the ground is with the information that's here, even though none of the information that's here seems to correspond with forces, times, or momentum. And that's because I can count on the fact that you have learned other things in physics that should help you get to what you need to answer this question. So let me start by reminding you that you are supposed to have a handle on how to deal with something that is dropped. And know that when it's dropped, it will convert gravitational potential energy to kinetic energy, and that you could use that to figure out how fast it's going. Moreover, you should be able to reason that the ball recoiled in the opposite direction, probably with less velocity than it hit the ground with, since it doesn't go as high. But you should be able to reason out how fast it must have left the ground, because again, energy is conserved between the earth and the ball. That should allow you to figure out what the initial velocity was when the ball struck the ground and the final velocity was when the ball left the ground. Now, you might not know how hard the ground touched the ball or for how long the ball was in contact with the ground, but you could use the information we just discussed to figure out the difference between the final momentum and the initial momentum. That is impulse. Now, to do so, you would need the mass of the ball, something that would give you the final piece of what it would take to calculate mv final minus mv initial. That is the change in momentum of the ball. That's what I mean when I say you don't forget the other stuff you've learned. I suspect I can ask this question, and the only part that's new is the part where the ball's in contact with the ground. That's the only part where there's an impulse being applied to the ball from the ground, is when the ball's touching the ground. Now, the next couple of things I say shouldn't be a surprise. First, the impulse on the ball from the ground is upwards. That should be the direction of the impulse. The thing that is missing from all of this is that momentum is a vector quantity. You would have to decide whether upwards is positive or downwards is positive before you start the problem. Because it's clear to me that the ball changes direction, which means one of these velocities has to be pointed in the positive direction and the other one is pointed in the negative direction. But when you calculate impulse, it too has direction. It should not be a surprise to you that direction of impulse will be the direction of the force. Look, what is the direction of the impulse on the ball? It better be up. Why? Because the ground stopped the ball and then pushed it upwards. It should also not be lost on you that the impulse on the ground from the ball is downwards. The ball pushed downwards on the ground. And it also shouldn't be lost on you that these two impulses have to be equal and opposite. I know I talked about that just last week, so I know that that's review. There's a lot happening here, and I know I'm having to go a little bit fast. So, let's pay attention to the pieces, okay? First, let's zoom in here. Because all I care about is the collision part. Let me get this out of the way. Go away. There we go. So, first, do you want down to be positive or down to be negative? So down is negative. That means anytime something is moving downwards, I need to make that negative, and anytime something's moving upwards, I'm going to make that positive. Change in momentum is still final minus initial. The minus there isn't about direction. The minus there is the difference between the two. So, mv final minus mv initial. Now, I'm going to assume you know where I got the 14.1 and the 11.8. If not, I did mgh equals 1/2 mv squared. That's what I did. Raise your hand if I need to go through that part. Okay. Well, the ball's final velocity is upwards. So 0.5 times positive 11.8. The ball's initial velocity when it strikes the ground is downwards. That's 0.5 times negative 14.1. The negative times a negative will make that term positive, and I will add those two momenta together. And I don't remember what the number is that I got, but I got 12.98. Well, 99 kilograms meters per second as my change in momentum. Any question about that part? Well, how long was the ball in contact with the ground? 0.02 seconds. This impulse had to equal net force times time. And we're told it was 0.02 seconds was the time that they were in contact. So if I want to figure out the net force equals the change in momentum divided by the time, or 12.99 divided by 0.02. And when I did that, I got a net force of about 649 newtons. That is a standard impulse and momentum question. Yes, sir. To get the two velocities, I used conservation of energy. So let's consider this side first, okay? The ball had a gravitational potential energy based on the fact that it was 10 meters above the ground. I'm going to set that equal to the kinetic energy it has when it reaches the ground. Now, this doesn't tell me what direction the ball is traveling because the velocity is squared, but it will tell me how fast the ball was going. I'll cancel the m's out first, and I'll recognize that I get v equals the square root of 2 times g times 10, which for the first ball is the square root of 200. Now, again, I should be doing plus and minus here because I'm taking a square root, and I don't really know which one is the right answer. That's why it's always plus or minus the square root. The square root of 200 is about 14 point something, 14.1. So it's plus or minus 14.1 meters per second is the velocity at which the ball strikes the ground. Now, in a similar way, the ball recoils. It has kinetic energy at the start, but makes it to a place that is 7 meters above the ground. So if I want to figure out how fast it was going when it left the ground, I'm going to take 1/2 mv squared equals mg times 7. So canceling out the m's, solving for v, I get the square root of 2g times 7. This is the square root of 140, which is about 11.8. I make this expressly positive because the ball went upwards. Now, folks, I've said this to you before. I'm going to reiterate it. If you drop something, the time it takes to reach the ground is the square root of 2h over g. This is not the first time I've said this to this class. It's not in the curriculum, but if you memorize it, it'll make things faster. Do you realize that we just used the same thing over here, that v equals the square root of 2gh? We used it twice. That is both how fast something's going when it reaches the ground if you drop it, or how high something goes if you launch it from the ground. Am I telling you to memorize it? No. Am I saying you'll be faster if you do? Yep. You will. They're just consequences of the kinematics equations, but they're worth noting. Okay, just so you know, a big, long, drawn-out definition for collisions. And it has stuff in it like, in an isolated system experiencing no external forces, the net change in momentum of the system will be 0. That really doesn't tell you enough for you to fully understand anything about what that means. So let me just boil it down for you, because collisions are relatively straightforward. In a collision, the momentum before the collision is equal to the momentum after the collision, because in nature, momentum is conserved. And it's not transformed into other kinds of momentum. There's just momentum. mv. In nature, momentum is conserved. So anytime one object touches another, there's a transfer of momentum. Because anytime there's a force, there's an impulse. So all interactions conserve momentum. Now, there's going to be a lot of pieces to this, but it really comes down to two objects at a time coming into contact. So I have one cart and another cart. I don't know what they're doing, but they're going to collide. And in that collision, afterwards, there will probably be two carts, and they're going to be doing something after the collision. I don't know what. I'm assuming this collision, they bounce off of each other. I'm just making it up because I don't know the answer. As a demonstration goes, though, there's always a before and an after for every collision. There's what they are doing just before they touch. We say the instantaneous moment before the collision. And there's what's happening after they touch, the instantaneous moment after the collision. When we talk about collisions, we are talking a small period of time. So there's a thing that happens just a moment before and a thing that happens right after. When we look at a collision, though, the momentum before, which is the sum of all of the different momentums, no matter how many objects, there could be 100 objects, doesn't matter. We add up all the momentums before, it has to equal all of the momentums after. The individual amounts can change, but the total stays the same. Now, that doesn't mean that the objects all stay the same. These objects can be sticking together. They can be transferring pieces of mass between one and another. It's saying that the momentum of every object added up before has to equal the momentum of every object added up after. Every other variable can be changing the whole time, but the momentums have to equal before and after. And we're going to focus on relatively straightforward examples. But I want you to understand that it's not the collision that's the hard part. It will be the follow-up to the collision that'll be the hard part. So let's take a look at a very straightforward collision question. One that could easily be answered with what we know already. I'm going to say that the two cars during their collision join together. There's a coupling between them and they have a combined velocity. This type of collision has a special name. First, it's inelastic. All collisions are inelastic unless you are told otherwise. All collisions are inelastic unless you are told otherwise. Inelastic means that kinetic energy isn't conserved. That's what inelastic means. Kinetic energy isn't conserved. All collisions in nature are inelastic, except for like atomic collisions. This one is perfectly inelastic. That phrase, perfectly, means the two objects join together. So they can tell you the objects join together, or they can say it indirectly by saying they have a perfectly inelastic collision. If they say that, they're telling you that the objects joined together. Numbers to this, let's say that the first car is 5 kilograms and it's traveling at 5 meters per second, and the second car is 10 kilograms, traveling the other direction at 2 meters per second. So we've got some numbers to work with here. Conservation of momentum generates one equation. Hopefully that's enough. But it can only generate one equation. We set the momentum before equal to the momentum after. So there can only be one unknown. In this case, assuming the cars stay the same mass, the unknown will be how fast they're going after the collision. So one thing I don't know. They join together, so how fast are they going? And in what direction? I don't know. We're going to find out. So to solve one of these questions, before you start, I would encourage you to draw in an arrow to indicate what direction you're calling positive. Now you guys do realize I'm totally putting a framework in front of you, right? I'm drawing little pictures of the cars before and after. I'm putting a dividing line between them to separate out the impact moment. And where the impact moment is, I'm putting an arrow to indicate what direction is positive so I can be consistent. I drew a line down the middle because that's my equal sign. Whatever's on the left, that's the equal whatever's on the right. I'm giving you a framework to solve the collision part of the problem, a place to hang all the numbers. Because the next thing I'm going to do is say that object 1 times velocity 1 plus object 2 times velocity 2 has to equal object 1 times velocity plus object 2 times velocity. Those two velocities have to be the same because the objects join together. And now I'm going to start putting the numbers in. M1 was 5 times V, which is 5, plus M2 is 10, and V is negative 2 because it was going the other way. Can't forget that negative. That'll screw everything up. And you understand that's what I'm going to try and do, right? I'm definitely making stuff bounce off. I'm definitely making stuff change direction. Force you to think about it. This has to equal, and I will often do this on a perfectly inelastic collision. I'll join them together. So they have one mass. That's 5 plus 10. They are now one item. So I usually won't write them out separate. I'll say they are one item with one velocity. That's very common for what I will do when I solve these. Now the left side is 5, right? 25 minus 20. So 5. And that has to equal 15V. So at this point, I can solve for the one unknown. I can say that V equals 1/3 meter per second. That's how fast the system is going after the collision. They join together and are moving to the right at 1/3 meter per second. Any question about this? Yep.
So if it was V equals -1, that means it's
moving to the left. Yep. And that's what you guys will have to be able to do. Not only tell me how fast it's going after the collision, but in what direction, which means interpreting that positive or negative answer. Now, the next thing I'm going to do is not teach something new. I'm going to tell you what I'm going to do in addition to this. There are like 3 follow-up questions here that have nothing to do with collisions that I would do just to see if you're really paying attention in physics. For example, I would ask for the impulse on car 1. Did car 1's momentum change? Did it have a momentum before and a momentum after? Are they the same? Then car 1 had an impulse. I could have you calculate it. The change in momentum of car 1 would be 5 times 1/3 minus 5 times 5. That's the change in momentum of car 1. Now, I could definitely make you tell me the impulse on car 2. Which, based on what I'm looking at here, is going to be 10 times 1/3 minus 10 times -2. Now, if you're really paying attention, you understand that I would do this purposefully to show something. And if you're really paying attention, you realize what that is. Now, it's hard to see the big statement for this without getting the numbers here. Really hard to see it. But these two things have to be equal and opposite. They have to be. Listen carefully to this sentence. I'm going to use the simple words as possible. If the momentum of the system doesn't change, then the change in momentum of one car has to be equal and opposite to the change in momentum of the other. That has to be true. So we'll work this out. This is 5/3 minus 25. By the way, 25, I don't know if you know this, is 75/3. I got common denominators so that I can write this out as -70/3. Am I cool so far? Any question about that? If you're wondering where I'm going with that, well, 10/3 minus -20. Well, that's, if you don't mind, plus 60/3. Right? 20 is 60/3. Common denominators. I love fractions. Love them. Because this is 70/3. Of course it is. It has to be equal and opposite. They have to sum to give me 0. There's no change in momentum of the system. So any change registered by one has to be an equal and opposite registered by another. I would make you do that follow-up question just to prove it. If I want to know the force, I tell you how long they're in contact for. Now, question 3 is the one you're going to be the most upset about. I'm going to ask all about energy. Compare the energy after the collision to the energy before the collision. How much energy was lost during the collision? What is the percentage of energy after the collision? What is the percentage of energy lost? I am talking about kinetic energy. And to figure this out, you calculate the kinetic energy after the collision and compare it to the kinetic energy before the collision. I'm not asking very much. Before the collision, the kinetic energy is 1/2 mv squared for the first car, plus 1/2 mv squared for the second car. Kinetic energy. 5 squared is 25, times 5 is 125, divided by 2 is 72.5. No, it's not. I didn't divide by 2 correctly. I'm sorry. You should expect more of your teachers. So I'll write it as a fraction because I'm at a loss for words now. It's 62.5. Not 72.5. Sorry. Plus, 1/2 times 10 is 5. 2 squared is 4. 5 times 4, that's 20. And I could add those together. I know how to do that. That would be, let's see. 20, that'd be 40 halves. That'd be 165 halves. Joules. After the collision, 1/2 times 15 times 1/3 squared. Well, that's 1/9. So that's going to be 15 divided by 18 joules. 1/3 squared is a 9th. Half of a 9th is 1/18. 15 over 18. Is it clear the energy is less after the collision? I mean, 15/18 is less than 1. 15/18 is what? 5/6. Is that right? I love fractions. Love them. Why? Because I'm not scared of them. I used to be. I am no longer. There's energy lost in every collision. Now look, I did all of this really fast, not because I'm expecting you to be this fast, but because I'm expecting you to understand when you want to calculate the energy before, you add up the kinetic energies before. If you want to calculate the kinetic energy after, you add up the kinetic energies after. We've done this. We did this last chapter. Calculating kinetic energy isn't hard. There's a formula for it, and energies add together. Kinetic energies will always be positive. All the things we know from last chapter. So yeah, find out how much is missing. You subtract them. Find their percentage. You divide them. Things like that are things you know how to do from algebra. You're supposed to know what percentages are and such. I'm not going to belabor that because it's not that important. You should be able to analyze the energy. And you'll know you've done it right if the final energy is less than the initial energy, because these are all inelastic collisions. Now, having them stick together is nice. If they don't stick together, it's not really much different. Consider the exact same setup. The thing about them not sticking together is that you really don't know what happened. And there's really no way to find out. If you have a collision and it's merely inelastic, it's not perfectly inelastic, then momentum can only generate one relationship. 5 times 5 plus 10 times -2 equals 5v1 plus 10v2. That's all I can figure out. That's all I can state if they don't stick together, that they will have some velocities. You'll notice you can't solve that for anything. I generated one relationship, but 2 unknowns, which is frustrating, right? If I want to have a question like this, I'm probably going to have to give you one of these in order for you to be able to solve it. Because conservation of momentum can only tell us one equation. It can only give us one piece of information. So it can't ask for 2 things. Yes, sir. Kyle, do you have your hand up? So be aware that they have to give you quite a bit of information if they want you to solve something like this. And those of you who have started the homework realize they do. They give you a bunch. They say what happens after the collision to one of the cars. On the other hand, there is a subset of collisions that are called elastic collisions. Elastic, if you see the word elastic, somebody said our book uses the words perfectly elastic, but that's really just being redundant. The word elastic is enough. In an elastic collision, kinetic energy is also conserved. I did not say energy. I said kinetic energy is also conserved. Energy is always conserved. It's just transformed from one type to another. But in an elastic collision, kinetic energy is conserved. Truth be told, there aren't really any elastic collisions in nature that you can observe. Because if people think like billiard balls have elastic collisions, they don't. If you hear them, then some energy was turned into sound. So it can't be elastic. Typically, elastic collisions occur at the subatomic level, between particles, maybe between some atoms. So ions sometimes have elastic collisions. That doesn't mean that they won't say, assume the problem is elastic. And if they do, then it generates more information. You get to say 1/2 times 5 times 5 squared plus 1/2 times 10 times -2 squared equals 1/2 times 5 times V1 squared plus 1/2 times 10 times V2 squared. If it's an elastic collision, then you could be expected to figure out V1 and V2 because it generates two pieces of information. However, guys, let's be reasonable here. Do you realize how long it would take one of you to solve one of these? No matter what, you've got two equations and two unknowns, and one of them is a double quadratic. There's only one way to solve it. One way. You solve the top equation for V1 and plug it into V2 in the other equation, and that's still hard. This is easily 10 to 15 minutes of math if you're good at it and don't make any mistakes. So how likely is that on the test? It's that likely. You got it? They're not going to make you do a long, involved algebra process like this. It's too time consuming and it's testing your math skills more than your physics skills. If you want to know how I'm going to figure out whether you know this or not, I'll tell you how I'm going to do it. I'm going to give you one of these velocities. I'm going to ask, what is the velocity of the other car after the collision? And then I'm going to ask, is the collision elastic? I get to know whether you know the same things that I'm asking or not. It tests the same knowledge. But by me giving you this velocity, I'm giving you a method to figure out this velocity using just conservation of momentum, which you know has to be true. And then when I give you a follow-up question like, is this collision elastic? Well, then you don't assume these are equal. You ask, are they equal? You work out the right side and you work out the left side and you figure out whether they're equal or not. If they're not equal, then it's not an elastic collision. And if they are equal, well, then it is. Do you see how I get to test the same thing, but now the problem becomes about a 2 to 5 minute question instead of a 10 to 15 minute question? So what you must understand is that an elastic collision has an equal amount of kinetic energy before and after.